We always talk about proteins being the building blocks of life, right?
Right.
Well, get ready because we're about to dive into something pretty incredible.
Yeah.
We're talking about designing proteins, like scientists actually creating new proteins, not just, messing around with ones that already exist.
Yeah, it's a whole different ballgame. It's incredible. It's the kind of thing that wins Nobel Prizes.
Exactly. And that's actually what we're going to be talking about today.
Very exciting.
We're diving into this 2003 scientific paper.
Okay.
It's called Design of a Novel Globular Protein Fold. It was published in Science, so it's legit.
Of course, yeah.
And this paper, along with the Nobel Prize organization's press release, is really going to be our guide as we unpack this whole scientific revolution.
This paper is huge because it really marks a turning point in how we look at proteins. It's like, imagine if you were trying to understand every single thing you could build with Legos, but you could only use sets that already existed.
Oh, wow.
That's kind of where we were with proteins. We could study them, maybe tweak them a little bit.
Right.
But design a brand new protein from scratch? No way.
So then walk us through this research. What makes it so revolutionary?
So the scientists, they sat down and they designed a protein totally from the ground up.
Right.
A protein that, like I was saying, had never existed in nature. They called it top 7.
Yeah.
And it wasn't just some random protein. They actually had a specific shape in mind for this thing, like a 3-dimensional puzzle.
Oh, wow.
A puzzle they were inventing the rules for as they went along.
So how do you even begin to do that? Proteins are so complex, it just seems impossible.
It is incredibly complex. You've got these chains of amino acids all twisting and folding, and the way they fold that determines what the protein actually does.
Right.
And that folding process, it's nuts. It's all these different forces at play.
Really?
Attraction, repulsion, whether it wants to be near water or hide from water. And it's all happening on such a tiny scale.
So how on earth did they figure out how to control all of that?
Well, they basically had to become like digital sculptors.
Okay.
But instead of clay, they were sculpting with molecules.
Wow.
They used these really complex computer programs to kind of model and predict how these amino acid sequences would behave.
So like a very, very advanced game of Tetris?
Yeah, like molecular Tetris.
Exactly. And they had this program, Rosetta Design. That was like their secret weapon, right?
Yeah, Rosetta Design was key. They basically gave it information about what they wanted top 7 to be like, and it went to work, testing out all these different amino acid combinations.
So it was like their molecular architect.
Basically, yeah.
But this was 2003, right?
Yeah.
I mean, that's way before all the fancy AI we have now. So it wasn't just push a button, design a protein.
Oh, no, definitely not. They had to work really closely with Rosetta Design. It was a back and forth thing. They'd generate some models. Rosetta would try to optimize them based on all those, energy calculations. And then the researchers, they'd look at the results, make some tweaks, and then do it all over again.
So it's amazing that they were able to actually create top 7 in the lab after all of that. How did they even know it worked? That it actually folded into the shape they were going for?
Well, they used a technique that's kind of like taking a picture of a molecule.
A picture of a molecule?
Yeah, and what they saw was amazing. I mean, this was groundbreaking stuff for the time.
Yeah.
The paper mentions a 1.17 angstrom difference between the model and the actual structure. Now, to give you an idea of how tiny that is, an angstrom is 1/10,000,000th of a meter.
That's unbelievably small.
It is. And that level of accuracy, nobody had ever seen that before.
Yeah.
It proved that their calculations were incredible and that we could actually design these complex protein structures. It wasn't just a dream anymore.
And this was really just the beginning.
Right.
Because years later, this research earned David Baker, the lead author on that top 7 paper, half of the 2024 Nobel Prize in Chemistry.
Wow. Yeah.
For computational protein design. The other half went to the team behind Alphafold 2. Which, if you haven't heard of it, it's this AI that can predict protein structures. And it's incredibly accurate.
It's like they're two sides of the same coin.
Exactly.
So on the one hand, you've got designing proteins from scratch.
Right.
And then on the other hand, you have this AI that can take any protein sequence and tell you what it looks like.
It's mind-blowing. The possibilities seem endless.
Oh, they are.
But before we get ahead of ourselves, let's go back to top 7 for a second. How did they actually build this protein? It's one thing to design it on a computer.
Right.
But to actually create it in a lab.
It's like, when you're building a house,
right.
You wouldn't just start with a big pile of wood and nails and hope for the best.
Yeah, that's a recipe for disaster.
Exactly. You'd want some kind of plan.
A blueprint.
Right. And that's kind of what they did with top 7.
All right.
They had this target fold in mind, like the blueprint. for the overall shape they were going for. But instead of like starting from scratch with individual amino acids, they used what I like to call nature's toolbox.
Nature's toolbox. What's that?
So they went to this amazing place called the Protein Data Bank.
Okay.
It's like this huge library of 3D protein structures that we already know about.
No.
And they looked for little protein fragments, little pieces that kind of resembled parts of their top 7 fold.
So they were like rummaging through a bin of Legos looking for the right pieces.
Exactly. And that's where Rosetta comes back in.
Okay.
They use this process called fragment assembly. It's like putting together a jigsaw puzzle, but in 3D.
Wow.
They started with this rough 2D diagram of the top 7 fold, and then they used Rosetta to try to fit those fragments from the protein data bank into a 3D model that actually matched their blueprint.
Okay, so they have their 3D model, but it's made up of these like borrowed fragments.
Right.
It's not the actual sequence they wanted for top 7.
You got it. Think of it like having the frame of a house. You got the basic structure, but you still need to add the walls and the roof and all the details that make it livable.
Okay, so like the amino acid sequence.
Precisely. And that's where Rosetta design really shines. Remember all those forces we talked about earlier?
Yeah, the attraction and repulsion and all that.
Yeah, all of that. Rosetta design took all of those into account and tried to find the amino acid sequence that would not only fit within that scaffold, but also fold correctly.
So it's back to molecular Tetris, but with way higher stakes this time.
Right. And the researchers had to guide Rosetta design the whole way. It was a constant back and forth, refining the structure and the sequence until they got it just right.
It's incredible that they were able to do that. And the fact that the final top 7 structure was so close to their model.
It just shows how powerful this whole process is.
Yeah. They basically taught a computer program to help them design a protein that doesn't even exist in nature.
It was a huge moment for protein science, and it laid the foundation for even more amazing tools like Alphafold 2.
Oh yeah, Alphafold 2. The protein structure prediction superstar.
Yeah.
But I'm still trying to wrap my head around this connection between designing proteins, like with top 7, and predicting their structures.
Yeah.
They seem like two sides of the same coin, but I don't quite see how they fit together.
It's pretty cool, actually.
Yeah.
So by figuring out how to design a protein from scratch, Baker and his team learned so much about how protein folding actually works.
Right.
Like the relationship between the amino acid sequence and the final 3D structure. And that knowledge became incredibly valuable for developing things like Alphafold 2.
So it's like Baker's work provided the instruction manual, and Alphafold 2 is able to read it and understand it.
Exactly. It's this awesome combination of computer science and our understanding of how nature works.
Yeah.
And together they've opened up so many possibilities for new medicines and materials.
Okay, so let's talk about those possibilities, because the Nobel Prize press release mentions some incredible applications for protein design.
Yeah.
What are some of the ways this technology could actually change our world?
Well, for starters, imagine being able to design proteins that could act as super precise drugs that go right to the source of a disease without harming healthy cells.
Wow, so like a guided missile for disease.
Exactly. Or how about vaccines that are even more effective and have fewer side effects?
That would be incredible.
Right. We could prevent diseases so much better.
That's amazing. And it's not just about medicine, right? You mentioned nanomaterials earlier. What's that all about?
Things get really wild when you start thinking about nanomaterials.
Okay, now you've got me on the edge of my seat.
Yeah.
Give me some examples. What kind of crazy stuff are we talking about?
Okay, so you want those crazy nanomaterials.
Yeah, lay it on me.
How about like self-healing materials?
Okay, now you're talking. Like right out of a movie, your phone screen cracks and then poof, it's good as new.
Exactly. That kind of thing could totally be possible with protein design. Or what about super strong but crazy lightweight fabrics?
Okay, so now we're talking about clothes that are lighter than silk but tougher than steel. Sign me up. But let's not get too carried away with the future fashion here. We were talking about enzymes that can break down plastic.
Right. That's a big one.
That's huge. Imagine a world without all this plastic pollution. Just these little protein machines cleaning up after us.
It's incredible, right? Or how about proteins that capture carbon dioxide right out of the air?
Okay, so we're talking about fighting climate change with proteins. This is amazing. It sounds like this technology could actually help solve some of the biggest problems we're facing.
I think it has the potential, definitely. And this is still just the beginning. We're really just starting to understand what protein design can do.
It's like we've opened this door to a universe of possibilities.
Yeah.
It all started with those scientists back in 2003.
It's true.
Taking this huge leap into the unknown. They had this vision, this drive to create something totally new. And look what happened.
It's pretty inspiring.
It is. And now we can design proteins that are just as complex as the ones found in nature. We can even create proteins that nature never even imagined. I mean, that's mind-blowing.
It really does make you wonder, what's next? What will we be able to do with this technology in 10 years? 100 years?
It's impossible to know for sure, but I can't wait to find out. Well, that's the amazing story of protein design. We hope you're as excited about the future of this field as we are.
Absolutely.
And hey, next time you come across a big scientific breakthrough, don't be afraid to take a deep dive. You never know what you might discover.
That's right. Never stop learning.
Until next time, stay curious.